Today we will be discussing about software and hardware co-design and program modeling. So we will be discussing on that particular topic. So first you should know what is co-design. Okay, you know what is hardware. It is a mechanical part of the embedded system, and software, which is the algorithm part of the embedded system. So you should know what is co-design, and later on we'll also study about programming modeling. Okay, so co-design means something which you are going to design simultaneously. So you have to design hardware, you have to design software. If you design them simultaneously, it is called as co-design. So when the hardware is being developed, at the same time you are also developing the software. So such type of design is called co-design. Okay. So today we will see first in the introduction why that hardware software co-design is important. Okay. So in earlier embedded systems, that is embedded systems which were developed previously, hardware and software were partitioned in the earlier stage itself. Okay, in the beginning only hardware and software were partitioned. So there were separate group of engineers for developing the hardware and separate group of engineers for developing the software. Okay, so you had two separate groups for developing hardware and software. Okay, so the engineers for a hardware group are responsible for developing or prototyping the hardware, and engineers for software group developed the software. So there was very less interaction between the two teams, and the development of the product was either serial or parallel. Serial means one after the other. So first you develop hardware, then you develop software, or you develop hardware, and that will be going on, and after that you develop the software. Okay. So series or parallel, separate groups were there. Parallel means both together but separate groups. Okay. So that way it was developed. Okay. Uh, so later on, after the hardware and the softwares were ready, they were integrated into a single product. Okay, and uh, this is how the hardware and software were developed in the uh, earlier type of embedded system. Okay, now in order to reduce the uh, time to market the product, you know what is time to market? More time required for the product to come to the market is called time to market. Okay, from the beginning stage till it is available for the user, that is called as time to market. So due to the increase in the competition of the market, and for reducing the time to market, okay, so a new approach for embedded system was developed, that is called as hardware software co-design. Okay, so hardware and software are designed simultaneously. Okay, we'll just look at the brief overview of what is this hardware and software co-design. Okay, so initially, when the product is being manufactured, okay, first the product requirement is learnt from the customer. So what type of product the customer wants? For example, washing machine. What type of washing machine? Okay, top load, front load, like that. So different types of washing machines are there. So depending on the needs from the customer, okay, the requirement of the product was converted into system level needs or processing requirements. So what type of system requirements are needed? So that product requirements are captured from the customer. Okay, customer will give inputs like what type of product is required. So at this stage, there is no separation between hardware and software, only functional requirement is specified, like what type of washing machine is required, front load or top load. Okay, automatic or manual. Okay, what type of washing machine is required. So functional requirement based on the function. Okay. Once the functional requirements are finalized, okay, these functions can be simulated and verified against performance and functionality. Okay. So once the functional requirement are specified, okay, once you know what is a functional requirement, okay, the system level requirements are transferred to the functions and which can be simulated against performance and functionality. That means uh, the system level processing requirements, like you need a tub for the washing machine, you need keypad, you need displays, you need software programs, okay, you need sensors, so many things you need for the washing machine. So system level requirements are given to the function blocks or functions, and these are simulated and verified against performance and functionality. So whether these sensors, functions, function requirements like your configuration of the tub and actuators, sensors, all these requirements suit good performance and provide nice functionality that is checked by simulation. Okay. Once the simulation is over, okay, next is the architecture design. So how you have to design your washing machine. Okay. So you here it is segregated into hardware and software in the architectural phase. In the functional phase, there is no segregation. All functional requirements are taken as one single entity. But when you move to the architectural design, you have hardware and software, separate entities. Okay, hardware requirements are fulfilled, and then software requirements are also fulfilled. Okay, so you have either a hardware or a software requirement. Okay, so the partitioning of the system requirements into hardware and software is based on the hardware software trade off or differences. Okay, so you segregate into hardware components and software components. Okay, so this is about the introduction to hardware software co-design and why actually such a type of design is required, that we have learned. Okay, why it is required hardware software co-design? Usually for reducing the time to market and to speed up the product manufacturing. Okay, the next topic that we are going to discuss is the fundamental issues in hardware software co-design. Okay, so if we consider the hardware software co-design to be a problem statement, so we may try to solve this problem by and in that process we may encounter many issues. So we need to solve these issues in order to implement the hardware software co-design. Okay, so we will see some of the issues that we face while we perform hardware software co-design in embedded system. Okay, first is selecting the model. First is the selecting the model. Okay, so we will see what is this selecting the model. How do we select the model for our washing machine? Okay, so whether you need a front load washing machine or whether you need a top load washing machine, what is the model, motor specification, tub specification, sensor specification, and all other things which we need for hardware and software co-design are to be specified. Okay, so we will focus on selecting the model. Okay, so first you should know why a model is required. So model is basically required for capturing and describing the system characteristics. Okay, for capturing and describing the system characteristics. So if you want to have a front load washing machine, then what should be its specifications, how it should be. Okay, that is given by the model. Okay, so generally speaking, model is a formal system consisting of objects and rules. Okay, so it consists of certain objects or components and certain rules or guidelines which have to be followed to build the model. Okay, so now what type of model you should have? The decision you have to make on the model is very difficult. Okay, it is very difficult to take a decision on what type of model you need for your washing machine. Whether you need front load or top load, okay, why you need that, all that is a challenging task for the manufacturer. Okay, so why it is a challenging task? The reason is simple. Okay, the objective with each phase changes. Okay, the you have functional phase and architectural phase, that which we have studied now. Okay, in functional phase, it is only a specification that is known at that stage. Functional of the system is the focus and not the implementation. So you may select the washing machine to be a front load washing machine depending on its quickness in washing. So if you want the washing machine to wash the clothes quickly and take up heavy loads, then you may take front load washing machine. Okay, uh, so that is a functional requirement, it is not the implementation. Okay, now after the functional requirements are finalized, you move on to the design aspect or architectural description or architectural implementation. Okay, so how do you finalize the architectural or implementation of the system? Okay, for that, the manufacturer has to look at the components that is required. So for the front load washing machine, what and all components are required? What is the motor specification? What is the tub specification? What are the types of sensors and actuators that can be used? What are the displays and what are the microcontroller and microprocessors that can be interfaced to control the tasks? All these are implementation aspects. Okay, so it is not the functional aspect. So depending upon the requirement of the manufacturer, he may change the model. Like for example, if 8051 microcontroller is suitable for washing machine, okay, he can use it. If it is not suitable, you have to change the requirement. Then if you change the microcontroller or microprocessor, functional aspect will also change. So you need to have the functional implementation. For that you will have raw materials or product raw materials like sensors, actuators. These are all raw materials for manufacturing washing machine. Okay, so sometimes the designer has to switch the model depending upon the requirement. Say some sensors are not available, then he has to change the sensors. Okay, that is about selecting the model. So if suppose yeah, it is not possible to build the front load washing machine, the manufacturer, depending upon the requirements of the architecture, may shift to top load washing machine. Okay. Second one is the selection of the architecture. Okay, this is very important. Selection of architecture. Okay, once the model is ready, okay, the model will tell the manufacturer about the system characteristics, but the model will not tell the manufacturer on how the system can be manufactured. Okay, so how you are going to manufacture the front load washing machine is not told by the model. It is only a functional aspect. Okay, suppose if you want to know how the system can be manufactured, you should have a specific architecture. Okay, architecture. So what kind of components should be there and what should not be there? All these are specified by the architecture. Okay, so you are going to build an architecture for the system in terms of different components and how to interconnect those components. Okay, so we will see what are some of the architectures available for embedded systems, and in that sense we can also discuss about architecture for uh, the washing machine. Okay, different types of architectures: controller architecture, data path architecture, complex instruction set computing architecture, reduced instruction set computing architecture, very long instruction word computing, and single instruction multiple instruction multiple data are some of the commonly used architectures that are used in embedded systems. Okay. Then what are these categories of architectures we have discussed? Okay. Some of the architectures like controller architecture fall into application specific architecture, means it is suitable only for specific applications. Okay, not all applications, only specific applications. Okay. General purpose architectures like CISC, so you can use in any type of application. And parallel processing class means everything is done parallel. That is VLIW, SIMD, MIMD. Very large instruction set, instruction word computing, and single instruction multiple data, multiple instruction multiple data. Okay. So now we will discuss a little bit about these type of architectures. Okay. So first we will talk about controller architecture. Okay, what is this controller architecture? Controller architecture implements the finite state model. Okay, finite state model. So you should know what is this finite state model. Okay, finite state model has a finite or definite state. Okay, so you can change the state, you can move from previous state to next state. Okay, that is possible. For that you should have a state register and you should have some combinational circuits like AND gate, OR gate, so on. Okay, so the state register holds the particular state, that is the present state, and the combinational logics help in changing the states, or they create a logic for changing into the or switching over to the next state. Okay, that is about controller architecture. So finite state machine model is controller architecture. Next is data path architecture. So what is this data path architecture? In data path architecture, you have data flow graph. So you have a model based on data flow graph. Okay. So what is this data flow graph? Data flow graph. So data is flowing and it's in the form of a graph. So you have input and output, and in between input and output some calculations or computations are performed on the data. Input data, you are performing certain calculations or computations and you are producing the output. Okay, so certain specific number of computations are there between the input and the output levels. Okay, so what is a data path? Data path is nothing but it is a channel between the input and the output. Okay, so what and all things should be there in the data path architecture? Okay, so some registers, control registers, register files, memories, ports with high speed arithmetic units, so on. Okay, so what are these ports? So you have input and output. You need ports for input and output. Okay, these ports help the data path to connect. They connect to the data path using uh, They connect to the data path using uh, buses. Okay, multiple buses are there. Okay, so you have an arithmetic logic unit that are connected in parallel uh, with the pipelining support for bringing high performance. Okay, so you have a data path architecture. Okay, so data path architecture has got an arithmetic logic unit which is the data path itself. Okay, and it links the inputted output and facilitates the performance facilitates the uh, computations and arithmetic calculations that can be performed. Okay, next is finite state machine data path. So now you have studied about control architecture and data path architecture. So finite state machine data path is a combination of the previous two. Okay, you have a control architecture, along with that you have data path architecture. So a controller with data path is called as finite state machine data path. Okay. So we will discuss a little about finite state machine data path. So you have a controller as well as a data path. Controller generates a control output. Okay. Control input. Okay. Controller generates a control input, whereas data path processes the data. Okay, it is a processor. Data path is a processor, or it processes the data. So you may have an arithmetic logic unit in that. Okay, for performing operations. Okay, so it involves a central control unit or processing unit. The controller generates the control signals, whereas the data path processes the data. Okay. So data path has two types of I/O ports, out of which one is acting as a control port for receiving or sending the control signals from the and to the controller. And the second I/O port interfaces data path with external world for data path input and output. So basically, there are two ports for the controller. So one port is for the control signals and another port is for data. Okay. Control signals have to be moved from the controller to the data path and back from data path to the controller, as well as data signals have to be moved from the outside world to the processor and back from the processor to the outside world. So you have the second I/O port. Okay. So this data path is implemented in the form of chip, and I/O pins of the chip act as data input ports for the data path. Okay. Next is complex instruction set computing. Okay. So this architecture uses instruction set with complex computing. Okay. So complex operations can be performed using this type of instruction set. Okay, using a single instruction, you can perform complex operation. Okay, for example, you have a CJNE instruction. What is CJNE instruction? You have studied in 8051 and also you have studied in ARM. CJNE, combined jump not equal to instruction. Okay, so you can read a register value, compare it with a given value, and transfer the program execution to a new address if it is not equal. Okay, that can be implemented using a single instruction. So what is the advantage of using complex instruction set computing instructions? So program memory size requirement as well as number of memory accesses are greatly reduced. Okay. However, For implementing these type of instructions, certain silicon based microcode decoder is required for decoding this instruction. So in CISC processors, you have CISC instruction set, and to decode this instruction, you should have silicon based microcode decoder. Okay. So essentially, the data path for the CISC processor is complex. On the other hand, we have another set of instruction set processors like reduced instruction set computing processors or RISC machines. Okay, so they use simple operations, and execution of multiple RISC instruction is required for complex operation. Suppose if you have to perform complex operation, you can do it by CISC by using a single instruction, or you can do it by a RISC by multiple number of instructions. Okay, that you can do. Okay, then very long instruction word architecture. Okay, so very long instruction word architecture. Very long word instruction architecture implements functional units like ALUs, multipliers, etc. in the data path. Okay, so VLIW architecture packages one standard instruction per functional unit of the data path. Okay, so one instruction here again for one functional unit of the data path. Okay, okay. So very long instruction word, okay, implements multiple functional units like multipliers, ALU, all can be put together in the data path. Okay, so it packages one standard instruction per functional unit. Okay, multiple functional units can be connected, and one standard instruction is there per functional unit. Okay, that is very long instruction word. Okay, next we move to parallel processing architecture. Okay, so many multiple concurrent processing elements and uh, are present here, and each processing element may be associated with a data path containing a register and a local memory. Okay, parallel processing means many parallel processing elements may be present. Okay, and they may be connected to the data path using a register or a local memory. So you have single instruction multiple data and multiple instruction multiple data architectures as examples for parallel processing. Okay, so what is this single instruction multiple data? A single instruction can be executed with the help of many processing elements parallelly. Okay, single instruction, parallel execution, many processing elements. Now, the scheduling of this instruction and controlling of this parallel processing elements is performed by the single controller. Okay. The SIMD architecture forms the basis of reconfigurable processors. So if you want to have reconfigurable processor, which you can reconfigure again and again, okay, such processors use SIMD instructions. Okay. Compared to this SIMD processors, there is another type of processor called MIMD processor, that is multiple input instruction, multiple data. Okay, so different instructions can be executed at any time. Okay, so they help in multiple processing of data. Okay, so processing elements in a multiprocessor system communicates through shared memory and message passing processes. Okay, shared memory and message processing processes. So multiple processors, multiple controllers, and communication between the multiple processor system and mechanisms like shared memory and message passing. Okay, that is there. Next one is selecting the language. Okay. So programming language is another very important task for development of the embedded system. So programming language helps to know the computational model, okay, and how to map it to the architecture. For example, if you want to perform multiplication of two 16-bit numbers, you have to write a program for that. So computational model, multiplication of two 16-bit numbers is computation, and model for computation you have to develop using the programming language and map it to the architecture. Okay. To develop this programming model and for capturing the model requirements, there is no certain hard and fast rule. Okay. So this modeling model which can be captured using multiple programming like C, C++, C sharp, Java, etc. Okay. So you have software programming languages like C, C sharp, C++, Java, etc. And you have hardware languages like VHDL, System C, Verilog, etc. Okay. Both are used for programming, one for software programming, another one for hardware programming. Okay. Sometimes you have a single programming language for both hardware and software for capturing the model. Okay. Okay. Then certain languages are good for capturing the computational model, like C++ is a good candidate for capturing the object oriented model. Okay. That is an example. So how do you select a programming language based on the capturing ability? So to select the programming language based on the capturing ability, the language should be selected such a way that it can capture the model easily. Okay, or you can easily understand the model. For example, multiplication of two 16-bit numbers, okay, that is done by, you can write it in C program, you can write it in embedded C, you can write it in C sharp, or you can write it in Java. So which programming language helps to capture the model effectively and easily, that language should be chosen. Okay, selecting the language is about that. Okay. Next, we move on to partitioning system requirement into hardware and software. So till now we were discussing about capturing of the model, that is system requirements. And then we also discussed about architecture for implementing the system. Okay. Next we look at the implementation of the model. To implement the model, you have to segregate hardware and software. You have to separate the hardware and software. So this is very difficult thing for anybody who manufactures embedded system, because you have to make a wise and hard decision on software hardware partitioning based on hardware software trade-offs. Okay, so that we will discuss. Okay. So the next topic we'll take up in the next class, that is computational models in embedded system. Okay, computational model in embedded system. Okay, so that we'll cover up in the next class. So anybody is having any doubts in today's class? Are you able to hear me? Are you able to hear me? So are you able to follow what I taught today?
Yes, sir.
Okay. So we'll continue in the next class. Okay. And one more request is that those who have not submitted the assignment, please submit it at the earliest. Okay. So that I can correct it and put the marks. Anyway, your college might reopen on June 1st. Okay. So till then, you have sufficient time to complete other assignments like the second and third assignment, which will be given. Okay. So by June 1st, so you should be able to complete all the 3 assignments. So I will give it in advance. Okay. So you have to complete it and submit. Okay. So I have
Okay,
given the
sir.
first assignment and second assignment. Okay, that you need to write. Okay, third assignment will be given soon after this module completes, the fourth module. Okay, so some more topic, one more topic is, one or two topics are remaining in this chapter. After that, we will move on to the last module, fifth module. Okay, so we'll stop here today. Okay,
Okay, sir.
okay.